I'm happy to introduce our next speaker, Bedra. He's a senior software engineer at Cumberland DRW, and he will talk about security in software and design trade-offs. The talk is One Ring 3 to secure them all, competing with hardware enclaves. Hello, Bedra.
Hello, thank you. And thank you for having me. Really excited to have another well-organized virtual conference while we're kind of hitting the final pieces of COVID, hopefully. But this morning's presentation is meant to discuss what I think is a really important shift in security. We don't have them very often, but hardware enclaves are, and I think, a really important step forward to secure design and really kind of secure design foundations for things that may not live in a data center, which is a lot these days. But the focus of this talk is really about trusted execution environments. That's the really kind of the subset or the class of things we want to discuss right now. And what I mean by trusted execution environment is a place where you can run code or execute code, where you have an assurance of who has visibility into what's happening. Ultimately, we're trying to solve a specific problem, which is how do you solve the secure execution problem for critically sensitive data? And what I mean is, if you're encrypting, decrypting, signing, searching encrypted data, all kinds of stuff that revolves around sensitivity, how do we solve the kind of secure management problem? This is a kind of a unique problem. It has a lot of subtlety and a lot of things that can go wrong. It's a classically difficult problem to solve as well. Not only is the encryption itself and the choices of how you encrypt important, but the execution of that code in your environment, where the servers are kept, there's this giant class of problems that kind of cascades out of this. And there's also some other features around remote attestation or local attestation, making sure the software that you're running is supposed to run on this machine, hasn't been taken by somebody else. It's just kind of a pretty rich set of problems here. And for the typical set of server-based encryption problems, there's kind of two ways this happens right now. You have some process, and that process communicates over either a PKCS11 channel in the case of kind of traditional HSMs or hardware security modules, or as the cloud providers came online, they offered a kind of a more complete, more rich REST interface. So you can hit it over a REST API and have the same kind of functionality. You may not have the entirety of the HSM exposed. It's a kind of a subset of the HSM's functionality, but it's a much cleaner interface. You don't have to set up the communication channels that are a little bit cumbersome at times. And so we've come a little bit forward, but HSMs are still, they're still tough to manage, right? They're expensive. Redundancy is important to consider, but also hard to pull off. There's quite a few drawbacks here. And even though you may not do this over a network channel, maybe you have it over USB, you plugged it into a USB connection, or you have it on the PCI bus, if you talk to it that way. It doesn't really leave room for solutions that exist on, let's say, a mobile device, or a kind of Internet of Things piece of hardware that sits in an environment somewhere. So it wasn't a complete picture. It doesn't really solve all of our problems. And again, the cost is sometimes prohibitively expensive to pull off. So changing the model a little bit, we can consider building the trusted execution environment as a subset or a part of our program. And that's just really what the hardware enclaves tend to solve, or are trying to solve, which is how do we compute inside of our process and then kind of create an environment of trust that we can do the secure kind of critical operations around. So this is kind of the model shift. But unfortunately, not all these are created equal. And that's a pretty important part of this, is just fun understanding what each of these hardware enclave offerings does. So I'm going to walk through a little bit of the available options, meaning these are kind of the majority leaders of things that you can kind of get quickly. There are other things out there. I'm really trying to target the most applicative or the most broadly applicable options. Intel has their software guard extensions or SGX. AMD has a similar type of environment for secure encryption. ARM has an offering called Trust Zone. Apple has their Secure Enclave, which has actually been around, it's always been around for quite a while, but Apple's Secure Enclave is probably the most notable and probably one that if you've interacted with an enclave in the past, it's probably been one of the Apple enclaves because they've been so kind of fundamental and first class. And AWS has offered something recently called Nitro Enclaves, which offer a very similar type of functionality. It's worth noting, I don't have some of the other cloud providers listed here. It's not because they don't have an offering. It's that they build on top of some of the other offerings, right? If you're in Google's cloud or Microsoft's cloud, you're going to see, either some combination of SGX or AMD's SEV environment under the hood there that they're building on top of. So it is worth noting that it's not just AWS that has this offering. It's just that AWS has branded kind of their own special version of this. I expect to see more of that coming down the road as well. And what this does fundamentally is it represents a change in the threat model. And I think this is an important part of the conversation, is that the threat model has evolved or changed with the application of hardware enclaves. I took this picture from Intel's image archives. I think it demonstrates what's going on here quite well. On the left, you see the attack surface or the things that you can attack without an enclave, right? Effectively, everything running in your program all the way down to the hardware level, the process effectively itself can be attacked. So the attack surface is a little bit larger with a traditional application, whereas the attack surface with an enclave sits inside your application itself. So you can always make mistakes and leak data by programming incorrectly. But the process, the operating system, the virtual machine, potentially the things that manage underneath, those don't have any visibility or purview into that data anymore. And so you're effectively attacking the application itself, or maybe a potentially improperly programmed side channel, or the hardware itself. And I'll get into that a little bit, because I'm sure that if you're interested in this, you've seen some articles about speculative execution and some of the things that may affect this. And so I'll touch on that shortly as well. But if you think about the model or the redesign, your program can function almost as if it did before, with one caveat, and it's that you build a trusted execution part of your program. And I'll show you a demo at the end of this that kind of separates the two ideas and show you what the trusted side does versus the kind of your normal program code, and how you redesign your software in kind of small ways to make this work or take advantage. There are some vendors that say, no rewrites, no anything. You simply decorate your code and we'll go ahead and take care of the trusted execution. I think there's some interesting stuff there. But in terms of learning how this really works, we'll talk about the nature of untrusted code, the kind of gating mechanism or the hardware control, and then the trust execution environment or the trusted code execution. And we'll talk about marshaling data in and out of that environment, which is an important part of this kind of whole context. But first impressions are important to me. I took a look at all these and kind of gathered some ideas. And there's kind of three categories I want to touch on. And each of these three categories has kind of, to me, a distinct kind of leader in each category. The first is ergonomics. I think Apple wins here. Their SDK is first class. It's built in. It feels very batteries included. I feel like Apple's gone out of their way to make this just part of their environment. They've been supporting this on basically everything for quite a while now. And they really have put this kind of this foot forward, I think, earlier and more complete than some of the other offerings. So I think for ergonomics, Apple definitely has a leg up. In terms of broad application, I think ARM really has a foothold here, right? If you think about how many things ARM is used in these days, right? The not Apple phones, or even, in the Apple environment, there's still, some ARM there. But the non-Apple tablet and phone markets, the IoT markets, they have all of these system on a chip delivery mechanisms. I think ARM has probably one of the broadest reaches these days. And so if we're thinking about using the hardware enclaves, I think ARM's Trust Zone has applicability in a ton of places. So I think I would expect to see a lot more coming out of this world down the road. And I think the most in-depth and the most kind of deep offering in my eyes comes from Intel. They've solved not just the kind of typical encrypt decrypt sign inside of a secure enclave, but also some of the attestation problems of verifying you're running in the environment you're supposed to, things haven't been stolen. And it's not that other things don't offer this, but it's that Intel kind of built this along with the rest of the world. And so when I think about these kind of three things, touching back on ARM for a second as well, is the network is a really important piece of this, right? If you can't reach out on a network or you have an unstable network, having these things in process and on machine is one of those kind of shifts in how you think about designing software. And that's why I really think that the ARM environment has a pretty big advantage going forward. We're going to see a little bit more disconnected world or potentially unstable network world. But some considerations, and these are really important to consider as you're possibly choosing whether to use enclaves. Performance. We have to talk about this. This is definitely a really interesting piece. You can't get the same level of performance, of throughput, number of operations a second, as you would doing typical OpenSSL operations in your normal environment. Right? There's chip optimized compilation of OpenSSL. These operations are supported natively on the CPU. Your SHA operations, your AES operations, those are all, chip instructions at this point. There's intrinsics to cover it. The throughput and the general performance you get continues to improve. When you choose a hardware enclave, you're marshaling data in and out of a protected environment. You're going to jump protection rings in the case of something like SGX. So you have context switching, you have marshaling, and then you have execution instruction sets that are different from the normal CPU instruction set. While they try to optimize, they're not quite as optimized as the stuff that's been around forever. So you're going to take some throughput hits. There's a paper at the end that I'll link to that kind of talks about some of the impact and some of the considerations. It focuses on SGX, but it's kind of broadly applicable. You can consider the rules and some of the things that they're discussing to be pretty kind of ubiquitous throughout the enclave environment to performance hits, which includes the marshaling and the separate instruction sets. Also important to note, right? The threat model's changed, but it doesn't mean that the threat model went away, right? The threats still exist, and you need to update your threat model to correspond with the design of your software using an enclave, right? So you're thinking about different attack vectors, different things to fix, different things that need to be considered, right? And I think that's really important to call this out because microcode issues are one of those classes of problems that you have to consider now, right? The stuff that, really kind of fundamentally powers these enclaves is sitting at a deeper level, right? With SGX, it's at ring -3. It's in the Intel management engine. A fix could include a microcode update that you can patch through OS, or it might even include a BIOS flash, right? And so you're talking about downtime in a lot of cases. You have to patch, you have to reboot, you have to completely power cycle. It could mean hands-on in the data center in some cases. So fixing these kind of issues can be more cost intensive. It means you probably need multiple servers so you can deal with availability and patching life cycles. Just something to consider as you roll this out. You may not have that multiple CPU or multiple machine environment in an IoT environment, for instance. Maybe you put 2 chips on a board, but that gets pretty expensive. And so something to consider here is that those microcode issues and those instruction sets can be difficult to manage if a fix is needed. And in the case of Intel's SGX or really kind of the x86 instruction sets, there's still some vulnerability to the speculative execution attacks. It's not that all Spectre style attacks are relevant. There are still some that do impact, and you'll see some announcements that SGX is impacted by this particular class of Spectre vulnerabilities. So it doesn't mean that they've gone away. It means that we still need to consider them, and that patching is actually really important as these discoveries are made. And so it's really important, and that goes back to some of the microcode updates I talked about a minute ago, which is you've got to keep on top of patching in order to make this a reality. But I guess that really goes with any type of environment. There are some design trade-offs depending on how the enclave is designed and how it's used. Some designs rely on protection rings, like hopping from user land or kernel space into ring -3 in the Intel case. There are some designs out there that have separate chips that are entirely dedicated to this. Could be on the die of the CPU. It could be in a separate place, but they use kind of a different type of separation. But the protection ring is kind of one of the more common design choices. So you want to think about your threat model and what you're doing here to make sure that everything is working or designed as intended. Some implementations are gated by the vendor. What that means in this case is that in some deployment scenarios, when you're going to production, depending on how you want to use the enclave, you may have to register with the vendor, give them business information, give them information about what you're trying to do, basically registering yourself so that you can run inside of their environment, right? You're kind of a trusted vendor, and their universe of management understands who you are, can sign your signing keys and make sure you're kind of validated as a secure root of trust principle. That can be cumbersome from time to time. And, it would be kind of remiss to say it can be difficult to use. I guess is probably the best way to put this, is these are low-level constructs. They're not ubiquitous. They're not normalized yet. This is still kind of an evolving ecosystem. And so a lot of what you're seeing is going to be, a C level, C++, Rust, something like that's going to be the interface you're going to use to implement the direct interaction. It doesn't mean that you can't FFI this away and have all of your programs just integrate seamlessly with the layer you've written, but that layer is still going to be a little bit more low level than maybe the rest of your ecosystem. So there's some hurdles to getting started into using this stuff properly. And unfortunately, there's limited availability. And I don't just mean this from it's hard to get computers these days because chips are hard to get. I'll consider SGX for a minute. It's very easy to get SGX hardware on a desktop computer or a laptop, or some of the like prosumer pizza box, 1U servers. But as you move into the multi-socket, more enterprise grade server class, you don't find these. It's hard to order. And now Intel has indicated that the next generation of hardware is going to support this more regularly. There's a lot of signal that problem's going to go away. But when you're considering how to buy hardware, if you're not going into the cloud, you do have to consider, does this change what your fleet looks like? Does it change how you manage stuff in the data center? So it is also important to note that hardware enclaves, to me, right, I think is the key component in advancing how we think about secure software. It's yet another option. It gives us another tool, the tool belt. It's not for every piece of software. It's not going to solve all of our problems. If you have a raw throughput problem, this is probably not going to be your answer. There are specific problems that I consider here when I'm thinking about hardware enclaves. Solving the secret bootstrapping problem is probably one of the things I lean on most often here, which is, you might have a secret, or maybe you have a secret management engine, right? You still have the one thing that manages all of your secrets, but you still need a secret to get to all of your secrets. How do you secure the secret that gets all of your secrets? And that's that secret bootstrapping problem. I think this is a great way to solve the bootstrapping problem, right? If you were to think about a design all the way from the beginning, let's say you had a secret management engine and you needed a JWT to grant you, a token to access the rest of that secret management engine. You could realistically create a key pair inside the enclave, and then you could send that sealed key pair into the enclave and say, here's my JWT payload, sign it, and have that entire operation live in the enclave and produce you, a JWT string that you could send for authentication. That gives you that kind of bootstrapping from scratch solution to a problem, which I think is kind of compelling. The other thing is, of course, attestation, making sure your software is running on trusted environments, which there's a lot to say about where your stuff runs and who's running it, and making sure it's run in the environments it's supposed to, especially when it accesses sensitive information. So again, I think in the case of the tool belt, great options. And I think there's a tactical decision here, right? Secure design can consider this tactically when it's time to solve these difficult trust problems, right? This root of trust, anchor of trust. At some point when you're computing, you have to trust something, right? If you can't trust some kind of foundational thing, you can't run anything, right? Or effectively, you can assume that your world is compromised from the get-go. And there's plenty of things that would indicate that's true, regardless of how you do this. But practically, if you're going to run a piece of software and you're going to do business, you have to trust something at some point. And so I believe that this presents kind of that additional set of trust, additional set of options that we can consider when we're really kind of digging into this problem. So I want to go into a demo here. And so I will provide links shortly, but it's really important that we kind of go through the demo a little bit and then just kind of talk through how these things are designed. So I have a repository. There'll be a link at the end of this. You can go through all of it in detail. And there's an accompanying blog post. So it's a repository plus a blog post that explains kind of in detail what's going on. So if we run short on time here, there's a chance to kind of reread on your own time as well. So at the bottom, I'm going to run this program here. So the first thing I'm going to do is I'm going to provision a random number into my enclave, and it will come back encrypted. So if I do this and I say, I'm going to echo random, which you should never do, by the way, that's not really random. It's just random enough right now. And since I'm going to save a file called persistence.seal with a value of 32,350. And if I want to unseal that and print it back out, I'll run the unseal program. It will, provide that number back out to me. Just to make sure I'm not doing anything silly here and trying to fool you, we can take a look at the persistence seal file and just make sure that it is in fact not just a plain string in a file. It is encrypted. And if we check that out, ask it what it thinks it is, we can see that for sure, this is just some weird on random. It says it thinks it's a Star Office gallery theme. I don't know where that comes from, but certainly not what we're looking for here in terms of an encrypted file. So I think we're in good shape here. We are an encrypted file, but in thinking about how the enclave is designed. So this is something called a description language. It's effectively a C-style language for describing what the interface to your enclave should look like. This is what the calls of the interface exchange to your enclave is going to look like. For this program, I have something called seal and something called unseal. Sealing the data will give me some plain text in, and I'll get some sealed data out. The thing that's different about this, thing that makes it kind of not like a true C-style language, of course, are these stanzas that describe the different sections, but you see these brackets here. This is to let the enclave know which direction that we're marshaling data. And so in this case, we're going to say we're marshaling data into the enclave. I don't want this memory to be available outside the enclave. I don't want this shipped back out of the enclave. This stays. So into the enclave will be this uint8t pointer to plain text. And the reason why we're providing a size here is that we have some pointer. If we don't give it a size, if we don't give it some description of what we think it's going to be, it's going to assume the size of the pointer. So that's going to be incorrect in most cases. And so we need to give it a little bit of an additional information. If we're not passing a pointer, we can often exclude that, but a lot of times you're going to push some pointer value in, especially if you want to populate that data to push back out. And so again, we're going to return sealed data, and we'll give it that size to help understand what the size is on the way back out. Unseal, it'll look very similar to the first, just reversed. And when we run our compilation routine, this is going to generate header files that we can use to do our implementation. So the matching enclave implementation, and when I said that you have just a little bit of things to do in the enclave side of the world to change your program, this is it. This is actually the entirety of it. We have an EDL file to describe the interface and an implementation. And this implementation is going to call the SGX API or the SGX XDK to get things done. So I've mirrored what I've put in the EDL file into my seal and unseal. And if we go through, we can kind of go natively right into the SGX API, and you can see a little bit more information. There's lots of documentation here as to how it works, what to consider, what the parameters are, what to expect. Fairly well documented in terms of what the API expects. Sometimes hard to find information on kind of additional support, additional things that might go wrong. But you can sift through fairly quickly to figure out what the interface should look like. So we're going to call the native SGX seal data and the native SGX unseal data as part of our program. Next, I'll take you into the provision part, and we'll make it a little bit bigger here. So provision and unseal are the two things that we ran, right? So if we want to put a new piece of data, seal a new piece of data in our enclave. We're going to boot up a couple of things. Our persistence class is just a real simple wrapper on saving the persistence file itself. There's not much here. It's more just a little bit of a wrapper and convenience. And really the meat here is enclave initialization. This is going to call into SGX, say, I need to create a new enclave. Here are some parameters around how I want the enclave to be addressed. And then we'll figure out whether or not we can continue our program from there. So initialization is part of our program. It's part of the untrusted part of our program. So it's part of the app versus the enclave. Given this, there's one native call here, one call of the SGS API, which is create enclave. And that gives us a few options. We want to know what is the, there's a file name, and I'll talk about the file name in a minute. The debug characteristics. So are we in debug mode or are we not in debug mode? So debug mode will provide you a little bit more information about what's happening if there's failure. A launch token, which is an optional value, but ultimately it says, has this program run against this enclave in the past? And if it has, I can replay this token. And that's kind of proof that I've already authenticated or attested that this program can run inside the enclave. And so you can pass that back in to forego some of the additional checks that happen once it's been run. Something that lets us know whether or not this launch token has been updated. Because if it has been updated by the enclave, we want to make sure that we save it. So the next time we run our program, we can play the most up-to-date enclave. And that token is always updated and kept fresh. The ID of the enclave, meaning which enclave effectively number do we want to assign to this? We'll just see me use 0 as the global ID for everything here, but you can get much more detailed in a production implementation. And additional attributes that we're not going to use in this particular case. So we'll give it the enclave name, and I'll go back to what that was in a minute. I'm going to say in this particular case, we're always in debug mode. I don't want to run in full production mode because I don't have all of the registration done with Intel properly to make this work. We'll pass our token in, which we've gotten from our environment, our pointer to whether or not we're updated, and then our enclave ID. And of course, we're going to skip those extra attributes. And then the rest of this is managing whether or not the token's been updated and saving or persisting that token if it has. So a lot of fluff around really just one call to the enclave. If we have done that properly, right, and we're able to continue, so we have a successful call. If it's not, we're going to really kind of bail here because this program's entire purpose is to provision something or save something. So because we're going to do some kind of random number, the only other part of our program is we want to read a number. And this, in this case, is just going to be read from standard in, do some combination from string to integer, and see if that's possible, see if they've done the right thing. So it's just a small bit of sanity checking. And if so, we'll call this provision method above, which is going to do the real meat of our operation, which is going to make that enclave call to seal. So you can see here now our interface meets the boundary of what we wanted to do for sealing and unsealing. So in this case, we call seal. We check on the status of things, and then we print out what we've seen in terms of a result. So fairly simple operation here. I'm not dealing with marshaling anything more complicated than an integer. Packing a struct and serializing a struct across the boundary and then unpacking it. There's a lot of ceremony and complexity to that, which you'll have to do in a production application. But I really wanted to dive in and state just the things that are important about the enclave and how you communicate with it. Likewise, unseal has a very specific and familiar type of thing, right? We're going to do the same thing with persistence, the same thing with initialization. A lot of this will work the same. The only difference is we're not going to take some random number input. We're going to simply take the file from persistence. We're going to pass it in. So we're going to load that persistence, that seal file. We're going to call this time the unseal method. So feed that back into the enclave. So that encrypted blob goes into the enclave. We say, I want to unseal it, and I want you to return the data out that you've unsealed. And so we get that number back out and we print it. So this is kind of that round trip. You should never do this in production. Never take that plain text and just ship it right back out of the enclave. The point of the enclave is to operate on that plain text data within the enclave so nobody else can see it. This is more just showing the mechanics. So in your real world, what you want to do is operate on that plain text and produce some derivative data that you'll need that you can use outside the enclave. Because once you leak that through the side channel, through that marshalling, now the threat model changes again. Now it's your entire application, your entire surface area. So you want to be really careful about the design of that marshalling in and out, and be very sensitive to what's going in and what's coming out, and making sure what's coming out is always kind of scrubbed or safe for the environment. And that's pretty much it in terms of kind of a walkthrough of how this stuff works. And so there's a lot of nuance and subtlety to what I just showed you. I encourage you to kind of take a closer look at all of this. And in order to do that, let me pull up some links that will make this a little bit easier for us. So a few links and references. So the code I just showed you is in a GitHub repository. The link is at the top here. So everything you can do, you can compile on your own, you can try it out. Even if you don't have a SGX capable computer, you can run these in simulation mode and still use the SDK to simulate what's going on. And it will just use native OpenSSL commands under the hood to get that done. So you can still kind of play with this and see how it works. The third bullet point is a getting started guide, a way to install the SDK and the driver, just some kind of point in time snapshot, kind of here's how you build your environment up. It's targeted towards Ubuntu, but the links to the Intel repositories are there if you're not on one of those types of systems. The next thing is this post SGX sealing. This is a blog post that explains in a little bit more detail what I just described to you. How does this software work? How does the in and out of the enclave work? How do you describe the enclave interactions? A little bit more kind of static content to deal with how all that works. Next thing, we have a paper written about performance. I encourage you to read this. It's an important part of making these kind of design trade-offs is what is the performance impact of this application and how does it work? There's next few links are brochureware content. So kind of the vendor's description of what that enclave is, how it works, what are the features you can expect, kind of the high level, right? Just to kind of back up and provide links into the kind of entry of this whole universe. Important to read if you want to get started, important to read if you want to think about the content. And of course, last is a really important piece as well, which is the Open Enclave project, which it really attempts to make a uniform API across all of the different enclaves. I think this is going to be something really important to look forward to in the future, and something that you really want to lean on once it's really fully readily available and across all the enclaves, to build a kind of ubiquitous enclave-based environment across data centers and cloud providers and all of these different environments that where machine-specific code can be a hindrance to deployment. So I think this is going to be something to keep an eye on for the future. So I think that's going to be it for this particular talk. And I'll be around for questions. But I appreciate you taking the time out of your day, and we'll do the Q&A. And of course, feel free to reach out if you have any additional questions once you take a look at all this. Thank you.
Thank you so much, Aaron. Amazing topic. Honestly, I'm going to tell you, before the talk, I had a different idea of what you're going to talk about. I had no idea but this is all about trusted execution environment, right? This is the jargon for it. And you've just introduced to us the Apple framework, Intel framework, and it seems like there are a lot of frameworks. And for each manufacturer, it has its own framework, right? My question is to you, I suppose all of these manufacturers have absolutely different kind of APIs, right? Everyone has their different take on it. And if I'm right, on the mobile, when you touch the screen, that the biometric detection also runs in the mobile's secure enclave, right?
In most cases, yes, that's right.
Yeah. And as a software developer, I am going to just say, I need a touch, and that's all I use, basically. That's mostly. But what are the use cases for using these APIs? Because these are deeper APIs. What use cases can you talk about when we use
Absolutely, yeah. And so in the mobile universe, a lot of this is abstracted away from you. You can say, hey, store a secret, and it's going to just do this for you, right? The high-level APIs, this touched on the ergonomics part that I talked about, which is, I really do believe that Apple has done a great job of the ergonomics. Android's SDKs also provide some of these features, but depending on what hardware you're operating on underneath, you're going to get a different thing, right? So you have to be a little bit careful on, trusting exactly what's going on, because you don't know which provider or manufacturer is providing what type of hardware assurances. Whereas Apple, it's the whole experience end to end, and they control that. So when you say do this on Apple's environment, you know what you're getting. Outside of the mobile environment, though, in maybe a normal kind of server farm computing or personal computing environment, that secret bootstrapping problem to me is probably one of the most compelling reasons to think about this, which is how do I secure the secret that gets access to all of my other secrets? That is a notoriously hard problem. Lots of wishy-washy kind of vague answers to how to solve it. Nobody really has a clear answer. And a lot of times solve secret sprawl, but this part's maybe a different problem to solve.
Right. Yeah, well, I've got another question that came to my mind is blockchains. And what do you think? Because I feel like blockchains are, and especially, we have these coins, and coins have wallets. And is this already being used in the software industry for blockchain applications, Ethereum applications?
Yeah.
How does this connect to the story?
Yeah. So I'll narrow my focus a little bit, not to blockchain, but to cryptocurrency. I work on a cryptocurrency trading desk. That's my day job. So I interact with the cryptocurrency markets most days. It's certainly being used in that space. It's being used in a lot of different ways. I can't go into too much detail about exactly how they're used, but if you look at some of the vendors out there, the hardware enclaves are definitely part of their offering. You see it in the custody space, you see it in transaction verification space. It would be probably improper to run the kind of problem solving, the hashing problem through this, because A, that's not necessarily secret. And B, you're gonna suffer that throughput problem. So, if you're trying to mine through an enclave, you're gonna have the wrong result, a wrong application. But if you're trying to secure assets, I think there's compelling things that exist there.
I see. So they are being used on wallets, but of course, when you're mining, you just use a absolutely concrete hardware for it. But for wallets, I suppose it can be used, right? Like these.
Again, I can't go to too much detail about exactly how and why you might consider that, but if you look at the vendors in the space, you're going to see hardware enclaves as part of the offering that a lot of the vendors in the space are advertising.
Yeah. Well, thank you. The links that you